Okay, we're going to carry on with the chapter on the bipolar junction transistors, specifically now the phototransistor, introduction to the phototransistor, and also transistor categories and packaging. Okay, if we go to our textbooks, on page 185, you see that I've underlined the introductory paragraph there again. A phototransistor is similar to a regular BJT, except that the base current is produced and controlled by light instead of a voltage source. The phototransistor effectively converts light energy to an electrical signal. We have discussed a similar device when we have done the diodes. If you can recall, it was also called a photodiode that operated similar to the phototransistor. Anyway, in figure 426, there are typical packages for a phototransistor, and of course also the schematic symbol for a phototransistor. Please note, if I go and look at the symbol here, you can see that the base terminal, the third terminal there, is missing. It's not always true. It's sometimes a 3-terminal device, so I can operate it as a normal transistor, a normal BJT. But most of the devices only has 2 terminals, and as we've read, it's light activated. So you can also see then that these 2 arrows pointing towards the transistor symbol indicates that this is a phototransistor. Alright, so make sure that you know the schematic symbol of a phototransistor as well. If you go back to the textbook, you can perhaps mark, as I have marked here, as well, the section. In a phototransistor, the base current is produced when light strikes the photosensitive semiconductor base region. The collector base p-n junction is exposed to incident light through a lens opening in the transistor package. When there is no incident light, there is only a small thermally generated collector to emitter leakage current, ICEO, and this dark current is typically in the nanoampere range, and we normally ignore it. When light strikes the collector base p-n junction though, a base current I lambda, see the Greek symbol there, is produced that is directly proportional to the light intensity. This action produces a collector current that increases with I lambda. So except for the way the base current is generated, a phototransistor behaves as a conventional BJT. As they also state here, that there is no electrical connection to the base in some cases, but you can also get a 3-terminal device. But if we look there at equation 4.1, the equation should look familiar to you. IC is equal to beta DC times I lambda. Remember, with a normal conventional transistor, it was IC is equal to beta DC times IB, but now the base current is generated by light intensity. Okay, a phototransistor. There's a typical phototransistor structure. Just to show you basically how it operates. You don't have to be able to draw this figure, of course, but let's have a look at figure 428, the phototransistor circuit, and then also typical collector characteristic curves. If you look at the collector characteristic curves, it should look familiar to you. Again, it is IC against VCE, and remember previously where we had different IBs here, now it's going to be I lambdas, né? So as the current increases at the base, in this case caused by light intensity, I can see also then that the collector current increases. So I can see that IC then is controlled by light intensity. as indicated there. Anyway, if I go back to the textbook, I can see there a phototransistor that I've marked over there. It fits in. Yes, there it fits in. A phototransistor can be either a 2-lead or a 3-lead device. A 3-lead configuration, the base lead is brought out so that the device can be used as a conventional BJT with or without the additional light sensitivity feature, because it's not designed that way. It should be a 2-lead configuration. The base is not electrically available and the device can be used only with light as input. In many applications, the phototransistor is used in the 2-lead version. Okay, but as I've explained to you now as well, the figure 428 shows a phototransistor with a biasing circuit and a typical collector characteristic curves, the same as we've done with the BJT. Notice that each individual curve on the graph corresponds to a certain value of light intensity. In this case, we can see that the units are milliwatt per square centimeter, and that the collector current increases with the light intensity. Now, phototransistors are not sensitive to all light. Just below figure 428, but only to light within a certain range of wavelengths. They are most sensitive to particular wavelengths in the red and infrared part of the spectrum, as shown by the peak of the infrared spectral response curve in figure 427. You can see there in the books as well. All right, then applications. There is an application for a phototransistor, relay circuit driven by a phototransistor. The phototransistor Q1 drives the BJT Q2 here in the first one, light activated circuit. Here you can see is my phototransistor, and you can see here it drives the base of Q2. As the light intensity increases, it will drive Q2 into saturation. The device will switch on, the relay coil will activate, and the switch will make contact. All right. A light deactivated, a different kind of circuit there in figure 430B. I can see here in this case, if the light intensity increases on the phototransistor, the current will be drawn away from the base of Q2, and Q2 will switch off, and the relay coil will switch off the relay contacts. Okay, so I've got a light activated and a light deactivated circuit as applications, as an example for applications that I can use for the phototransistors. Right, another application for phototransistors, if we go and have a look in our textbooks again, optocouplers makes use of some devices that you've learned up to this stage. As a matter of fact, an optocoupler uses an LED optically coupled to a photodiode or a phototransistor in a single package. Two basic types are LED to photodiode and the LED to phototransistor, as shown there in figure 431. So you have to familiarize with yourselves with these two basic optocouplers. Some examples are photocopper packages there in figure 432, A, B, and C there, dual inline, surface mount, ball grid, and so forth. What you should mark, however, is at the bottom of the page there is just below figure 432, a key parameter in optocouplers is the CTR. That stands for current transfer ratio. The CTR is an indication of how efficiently a signal is coupled from input to output and is expressed as the ratio of change in an LED current to the corresponding change in the photodiode or the phototransistor current. You will find in the basic problems at the end of the chapter there's a specific problem that addresses the specific point that has been mentioned here. Figure 433 shows a typical graph of CTR versus LED. Let's just get to that figure again. There you go, CTR versus CTR versus IF for a typical optocoupler. For this case, it varies from 50% to about 110% if you go and look here at the curve. Right up to there, and we can see there about 110%. Anyway, optocouplers, you can mark this last paragraph on page 188 as well, and show you that well, we can read it as well. Optocouplers are used to isolate sections of a circuit that are incompatible in terms of the voltage levels or currents required, because there's no electrical connection. For example, they are used to protect hospital patients from shock when they are connected to monitoring instruments or other devices, and they are also used to isolate low current control signal circuits from noisy power supply circuits or higher current motor and machine circuits. Okay, the next section, transistor categories and packaging. BJTs are available in a wide range of package types for various applications. Those with mounting studs or heat sinks that are usually power transistors, low power and medium power transistors are usually found in smaller metal or plastic cases. Still another package classification is for high frequency devices. You should be familiar with common transistor packages and be able to identify, of course, the emitter, base and collector terminals. Otherwise, you won't be able to use it in a specific design or circuit. Alright, the first category that is addressed is general purpose or small signal transistors, which is used for low or medium power amplifiers or switching circuits. The packages are either plastic or metal cases. Certain types of packages contain multiple transistors. In figure 434 illustrates the two common plastic cases and metal can package. Examples of multiple transistor packages. Some of the multiple transistor packages, such as the dual inline or the DIP and the small outline SO, are the same as those used for many integrated circuits. Typical pin connections are shown so that you can identify the emitter, base and collector, of course. The next category, power transistors. Here's some examples of power transistors and packages. Power transistors are used to handle large currents, typically more than 1 amp, and or large voltages. For example, the final audio stage in a stereo system uses a power transistor amplifier to drive the speakers. Figure 436 shows some common package configurations. The metal tab or the metal case is common to the collector and is thermally connected to a heat sink for heat dissipation. Notice in part E how the small transistor chip is mounted inside a much larger package. Right, now the last category, RF transistors. RF transistors are designed to operate at extremely high frequencies and are commonly used for various purposes in communication systems and other high frequency applications. Their unusual shapes and lead configurations are designed to optimize certain high frequency parameters. Alright, this concludes this section that I wanted to discuss. So please again make sure to read through The sections discussed examples, true, false quiz, certain action quiz, self-test, and importantly, basic problems. And for this specific section, basic problems number 31 to 36.